Okay, so in this video I'm going to cover the periodicity topic from, I think it's Unit 1 of the AS specification for AQA. The general topic looks at trends across period 3 in particular. So it's trends across period 3, which is which is sodium through to argon. But within that, these trends and everything that's going to be in this video is going to be directed to period 3, but you can of course apply that to different periods, so be aware of that. So first of all, it's fairly important that you can work out the electron configuration for the period 3 elements, and of course for all of the elements that you need to know, which I think is up to krypton, but for the period 3 of course. And the way it works is that really in the period 3 we're just adding in one more electron each time. Now the key thing of that is that if we start at the top here and we say we've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. If you imagine the sodium, we've gone through our first bit, so we've got our 1s2, 2s2, 2p6, we're now into 3s1 land. So we're in this first portion there. Now with magnesium it's going to be the same, we're going to have 3s2. Here we're going to have 3s2, 3p1. We're going to go into 3p2 with the silicon, 3p3, 3p4 for the sulfur, 3p5, and then 3p6 for the argon. And if you've ever looked at a periodic table, the way it's sort of split up into this kind of area like this, and if we draw on transition metals, we don't need them for this, but I'll draw them on anyway. Just imagine we've got this here, so 3, 4, 5, 6, and the 8th. Then what we've got these classifications of various blocks. So we call this the S block, this is the D block, and this is the P block. Down here you would have the F block, which is the lanthanides and the actinides, but you don't need to worry about those. But that's where you'd have the F, and that's your next orbital in. But S block, D block, and P block, and the way that works is that the electrons being filled, it tells you which orbital is being filled. So here, sodium, we're filling the S, as is true with magnesium. We put our S2. We then go over here with our aluminium, silicon, phosphorus, sulfur, chlorine, and then finally argon, filling the P. So if you can remember that, actually not too bad. And that's a classic question in an exam. They would say, what block is sodium in? It's in the S block. So that's fairly straightforward. Now what's quite important is it's the realization of actually how the electron configurations, how they affect really the various properties, and it's a lot of it is to do with the electrons, the properties that we see within this period of period 3, so across this period. Now, what you need to look at, what you need to know, are the trends across the period in the atomic radius. You need to know about the first ionization energy, and finally melting, boiling points. So I'm going to start with atomic radius, then I'm going to go on to the ionization energy and end with the melting and boiling points. So first thing then, atomic radius. Now, and the purpose really for showing those the electron configurations was that actually they give you a pretty good idea of what's happening. So if we look at this, the key thing is, because we're in this third period going across here, we can see that we remain in that third energy level the entire way across the period. So, and this is again is period 3 that I'm talking about. If I spell it right, that would probably help. Period 3. So what we've got then is same energy level, and that's really important, because the same energy level means that actually therefore we have same shielding. There is nothing being adding on, no extra shells to shield, so we're talking about the same shielding here. And that's really quite important. And what that means then is that if we have the same energy level and we're going across here, we've got the same shielding, well, there's no distance being added between the nucleus and the outer shell electrons. We're keeping within the same, very slight, but we're keeping within the same main energy level. But what we do find is that as we go across, we're adding an extra proton into the nucleus each time. And the key thing there is that with the extra protons, is that creates a greater attractive force, or a greater attraction between nucleus and outer shell electrons. So nucleus and outer shell, more protons equals stronger attraction. And that's very, very important. So as we go across this period, we find that more protons, blah, 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 we're getting a stronger attraction between these outer shell electrons and the nucleus, which means actually, as we go across here, the atomic radius is actually going to decrease, because the nucleus, the strength of the more positive nucleus, is going to draw in our electrons, and so actually we're going to find that across period, atomic radius decreases, and that's a really, really important thing. So across the period, the atomic radius decreases, and the reasons being that we have the same shielding because we're in the same energy level, yet we have more protons in the nucleus, therefore a stronger attraction to the outer shell electrons, which is pulling this in, so it's reducing this, meaning that we have a smaller overall atom. So that's really the atomic radius. That's what happens across, and why we have a smaller atom. The opposite is of course true. If we were to look at down the group, okay, as opposed to across, when we look at down the group as opposed to across the period, then actually here what we do is we do add more protons into the nucleus, not neutrons, but more protons, which means we have a stronger attractive force, but each time we move into a new energy level, and by moving into a new energy level means actually we're moving further away, and we're increasing the shielding. So actually down here, down the group, the size of the atom increases. Across the period, the size of the atom decreases. Therefore, up here is our smallest atom. I guess hydrogen actually would be the smallest atom, but if you're thinking about the actual periods and groups, it would be there, excluding hydrogen being sort of often floating around here. Okay, ionization energy. Now, ionization energy actually ties in. I'm just going to abbreviate that as IE. It's much easier to type or to write. It has a very similar idea to. It bases itself on atomic radius really quite strongly. And ionization energy is the energy required to remove an electron, to remove one electron. If we're talking about the first ionization energy, the energy required to move one electron. And so, for the sake of sodium, we will be looking at sodium. Remember to include your state symbols here to turn it into a sodium 1+ ion, an electron. And of course that's true of any of them, even ones that normally make 2+ ions. Magnesium's first ionization energy would be that. So still the same. We're going from atom to unipositive ion. So we're taking one electron away. Removing one electron. And you could always also write this as that, but I'm not the biggest fan. It's better to write it this way around, because when you do deal with half equations, particularly within redox, you can add them together much easier if you've got that there with the positive. But this is still correct. I would accept that in an exam, but I'm going to rub that out because I don't like it. So, first ionization energy. Now across the period, what's going to happen? So if we go across the period, and our first ionization energy is the energy required to take away the outer shell electron. Well, when you think about it, as I said, as you're going across here, we're adding more protons, we've got the same shielding, so those outside electrons are being held more strongly, and therefore it's going to increase. So general increase. So if we had a nice little axis here, we would see a general increase, and that would be fine. That of course is too easy, and it's not strictly speaking in what happens. We do find there's a general increase, actually that is still true, but there is a slight difference. So we go sodium, magnesium, then we go down, then we go silicon, phosphorus, sulfur, chlorine, argon. So we go up, a little bit down, up, a little bit down, up. And there's these things here, these quirks you need to know. So you need to know what's happening here and here. So I'll start with this one. Now this is the difference between magnesium and aluminium, and this one here is the difference between phosphorus and sulfur. So I'll start with magnesium to aluminium. Now, magnesium to aluminium. What we find here is that if you look at the electron configuration, so magnesium is going to be 1s2, 2s2, 2p6, 3s2. And if we look at phosphorus, help if that was actually the right element. If we look at aluminium, 1s2, 2s2, 2p6, 3s2, 3p1. So the difference here is we've got this 3p1 electron here that we don't in the case of the magnesium, and that's actually really important, because if you were to think about how this sort of looks on an energy scale, I'm just going from the 3s here, 3s is here, 3p orbitals are up here, they're at a higher energy level. So this is what we're finding for phosphorus here. We're having this extra, we're in this higher energy state here, which actually means that in general terms it's a bit further away from the nucleus. Therefore, because it's further away from the nucleus, it's actually easier to remove. Add on to that the fact that actually here we have more shielding. The reason for that is that within this we've got the shielding from the things below it. Here we've now got shielding from the 3s, whereas here we were adding to the 3s. So the 3s is acting and giving us a little bit more shielding, so this is easy to remove, and this is also slightly further away from the nucleus, again meaning it's easier to move. So more shielding, further away from nucleus. And what I mean by here, I'm talking directly in terms of the aluminium here, not the magnesium. So I'm saying aluminium has more shielding. Aluminium, this electron here, is further away from the nucleus. You could answer the converse possibly for magnesium, but I would stick with looking at aluminium. We're going to get rid of this now, and then I'm going to look at phosphorus and sulfur. Now this one, the phosphorus and sulfur one, I think is a little bit clearer actually as to how you have a difference between a dip there, the reason it goes down. But again, it completely relies on the electron configuration. So for phosphorus, 2p1, 2, 3, right. So for phosphorus, we have our s electrons filled. We're into our p single-headed arrows. Now p electron, p orbitals here. Okay, so this is phosphorus, and I'll do that in black, so that's a bit more clear. Now sulfur, we add in there. Now what you can see straight away here, because with my sulfur I have added an electron into here, this pairing now equals repulsion. And so you've got a bit of repulsion formed there, and that means that with this little bit of repulsion within this single orbital, we've now got just a little bit, it's a little bit easier to remove this electron here that I've just put in, because it is slightly repelled by what's there. So this becomes easier to remove, and therefore we have a dip down here. This electron is easier to remove than either of these from the phosphorus because of the repulsion there. So repulsion means that it's easier to remove the sulfur electron, therefore meaning that that process, sulfur to sulfur plus, it's easier to do, and so it drops down here. So we've got to drop down here, and we've got to drop down here, and that's your reason, repulsion present. Do be aware at this point that although I'm talking about it from period 3, there's nothing to say that in the other periods you couldn't be asked a question with relation to, I think it's nitrogen and oxygen here instead of our phosphorus and sulfur, or for beryllium and boron as opposed to magnesium and aluminium. And the same trends are true. You just got to knock it back one and talk about, in this case, the 2p4 it would be as opposed to the 3p4. So S 3p4 electron easier to remove than the 3p3 electron, and that's the key thing there between phosphorus and sulfur, and the reason why it goes up and then we get that dip down as it goes. Well, it's not quite as severe as that, but then we go back up again. So that's our general trend in ionization energies across the period. I'm not going to go into any more detail about ionization energies because I'm assuming at this point that you understand ionization energies, and maybe I'll do another video at some point on that. But at this point it's just to clarify really the changes in the general trend. Okay, so final point to look at then is the melting and boiling points. This one, there's a little bit more involved in this one. And I'm going to first of all write all the elements across the top. So we have sodium, we have magnesium, we have aluminium, we have silicon, phosphorus, sulfur, chlorine, and argon. So we have our elements right across there, our 8 elements. Now, before we do anything, the reason for this melting and boiling point, the reason for the change across the period is purely due to the bonding, and there is no general trend really. It does kind of go a bit all over the place. Well, there are little trends present, and the first one really is that we need to look at these 3. Well, at this point I would hope you've maybe done bonding, and so sodium, magnesium, aluminium. If you're not, then you've got GCSE knowledge there. All 3 are metals, therefore we have metallic bonding. In questions, state bonding. Okay, if you know the type of bonding, state it. Here we have macromolecular, so that is a covalent bonding going on. Same is true here in that we have covalent, but this time it is simple molecular, so again covalent, and this guy at the end is just what we would call monatomic. So, starting with these 3, metallic bonding. Now, metallic bonding is a strong type of bonding. It's a strong type of bond, certainly, and it exists because of the attraction between positive ions and that sea of electrons that you often hear about, or that's often used to describe it. So sea of electrons, positive ions, and the sea of electrons. Now in terms of across here, what we find is that here we have an increase in melting and boiling points. And the reason for that is that sodium we have a 1+ charge, magnesium we have a 2+ charge. I don't know why I've written +2, silly, but there we go. And for aluminium we have a 3+, so 2+, 3+. And what that means is that in terms of the sodium, I've got a singularly positive charge, and I've got these electrons around there, and I've got attraction between them, which is great. So there's attraction there, and that means that it has a melting point, which isn't actually too high for sodium, in fact. Magnesium increases. This is true of the boiling points as well. Magnesium increases. We've got a greater charge, and actually we've got a greater number of delocalized electrons, because it's always the delocalized electrons always come from the outer shell. So these are delocalized outer shell electrons. So more delocalized electrons and a greater charge here. And actually what's also true is we have it's a smaller ion too, because again, looking across the period, our size decreases, therefore we have a greater attraction between the two, between the magnesium and its delocalized electrons. Here, same again, smaller ion, greater charge, greater number of delocalized electrons. So the strength of metallic bonding increases across here. So we have an increase from sodium through to aluminium. Now, we hit silicon, and I'll just rub out all this. We hit silicon, and what we find now is actually it jumps up. Okay, particularly the melting point. There is a bit of a weird thing occurring when it happens with the boiling point, which I'm not going to go into, because actually I can't find an answer that I really like, to be honest. But for the silicon, we have a macromolecule, so it suddenly becomes a very, very big molecule with these strong covalent bonds. So strong covalent bonds, but also we have many strong covalent bonds. So we've now got a huge number of bonds present. Now, in order for this to melt, we must break all of those covalent bonds, and therefore it requires a phenomenal amount of energy to actually break all of those strong bonds, considering how many there are. That means that silicon has, it has a high boiling point as well, but it has a very high melting point. So it goes up again. Now you don't need to know exact figures for these, but you should be able to. Certainly, I've seen a question in the past where there was an axis drawn and there were points given on here, blah 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 blah, and it said here was nitrogen. It said put an X for where nitrogen's melting point, I think it was, would lie on these axes. And that really was an understanding question, in that you had to apply your knowledge and say, well, I know that nitrogen's a gas. I know that the type of bonding is present. And actually ended up being right down here, and you had a big area you had to just put it in. It could have been anywhere in here. So that's the only thing you need to be aware of these. You do not need to know absolute definitive values. That's the key thing. And if you were asked to plot a point on a graph like there, you would be plotting one maximum. So silicon, though, macromolecule, or we could also say giant covalent, many strong bonds, obviously need to be broken, and obviously those bonds need to be broken. That's the real point there. Many strong bonds, many strong covalent bonds need to be broken. You can potentially get sort of like 3 or 4 marks from just saying that portion there. Going across, we're now at phosphorus, sulfur and chlorine. Now at this point, actually, the melting and boiling points drop quite considerably. They really do drop, and the reason for that is that although we've got covalent bonding present, we've now got simple molecular structures, and we find that phosphorus exists as a P4 molecule, sulfur as an S8 molecule, and chlorine as the Cl2 molecule. So what we've got present now is actually, we're not really worrying about the covalent bond nature, because we're not breaking covalent bonds. We're talking now molecules, therefore we're talking, if I just draw it out like that as a P4 molecule, we're talking forces between the molecules, therefore intermolecular forces. Now, we've got no hydrogens, we've got none of our lovely elements that allow for hydrogen bonding to take place. Therefore, this force in between here is going to be van der Waals forces here. Okay, so we've got van der Waals forces between the molecules. What you should know by now, hopefully you've done bonding. If you haven't, then at some point you will. This will make more sense. If you've done it, brilliant, you should know this. Size of the molecule dictates the size of the van der Waals forces. The bigger the molecule, bigger the van der Waals forces. Ultimately, because we have more electrons present. So if we have a look at these molecules, P4, S8, Cl2, in simple terms, this is going to be biggest, this is going to come in second place, this is going to come in third place. Therefore, we're going to have a melting boiling point here, we're going to go up with the sulfur, and then we're going to go down for the chlorine. So we're going to find that is occurring. Okay, we're going to go up and then down, chlorine being the smallest. And actually that makes sense. Chlorine is a gas at room temperature. Sulfur and phosphorus, both solids at room temperature. So this must be that much lower. I can't remember what the melting and boiling point is, but it's pretty low. So simple molecular, as we're going here and then to here, we're having increasing, that's absolutely dire, decreasing van der Waals. And so the order I'm saying is I'm going from my sulfur to my phosphorus to my chlorine. So sulfur being here, so it's in a funny order, I know. So my biggest one going to my phosphorus, it's getting smaller, therefore it's dropping, going to my chlorine, even smaller, dropping again. So second biggest, going up to the biggest, to the smallest. Okay, so it's bigger molecule, therefore greater van der Waals forces, therefore more energy required to break the overcome the forces in between the molecules. Remember, the forces we're talking about are in between these molecules, intermolecular forces, not intra of any sort. So we're not talking bonding, we're talking intermolecular forces. So here, therefore, greater van der Waals forces present, therefore more energy required to overcome those forces, therefore greater melting and boiling points. Down here, much weaker forces in between, therefore much less energy required, therefore much lower melting and boiling points. Finally, we're over to the far right hand side, and we're at argon. And argon really, it follows the similar line to the previous three here, but we can't really include it because it's not a covalent, it's not simple covalent, it's just monatomic, which actually means that we have just single argons, all lonely, flying around. You should know argon, gas at room temperature, therefore it actually has a lower melting and boiling point than the chlorine does. Okay, much lower again, purely because of that reason. We only have single atoms here, and therefore the van der Waals forces in between the atoms are weak. So weak van der Waals forces, that's the key thing there. Very, very weak van der Waals forces. So, in summary, metallic bonding, the first three. Going across here, charges increase, therefore number of delocalized electrons increase, therefore strength of attraction increases, and also they get smaller, so we've got stronger attraction between ions and electrons, therefore boiling point, melting point increases. We hit silicon, and we hit a macromolecular covalent structure where we've got lots of covalent bonds that need to be broken, lots of strong covalent bonds, therefore things jump up. Boiling point's a bit weird, but don't worry about that. My thinking behind that is that when the covalent structure, when it's a solid, is broken down, that we don't no longer have covalent. I'm not sure what we would have in between the silicon atoms there, whether it would drop down to van der Waals forces, I'm not sure. But certainly when you have liquids here, we have the exact same, the bonding still exists there. We have that, still have quite a strong attraction between the ions and the electrons. So that's why if you were to look at this, and I'll put a graph up in a second, actually the aluminium's boiling point is actually higher than silicon, but don't worry about that. Talking about sort of general points here. Phosphorus, then sulfur and chlorine, we've got a simple molecular, we've got covalent again, but because it's simple molecular, we're talking intermolecular forces now. As the size increases, denoted really by the number, bigger the size. As the number's biggest, that means it's got strongest van der Waals, second strongest, third strongest, therefore the weakest, therefore higher melting point, boiling point than this one, which is higher than this one. Finally, argon, monatomic, therefore we have very weak van der Waals forces in between the atoms, which means it's quite easy to overcome those and therefore melt and boil. As I said, I'll just show you quickly a table, or a graph rather, as to what these melting and boiling points look like. Really the biggest graph of the world. I was hoping for slightly bigger, but there we go. And what we can see is, you can see these trends exactly as I've said. So certainly if we look at the melting points, sodium to magnesium is increasing, it's increasing to aluminium as well. It's going up to silicon again as we move into our macromolecular. We're dropping down to phosphorus, simple molecular. We're going up for sulfur, we're dropping right down for chlorine, then we're dropping again to argon. Same there is true of the boiling points. We've got sodium up to magnesium, up to aluminium, big jump there. That drop down to silicon's a strange one, which I would guess is something to do with the difference between the metallic and the covalent bonding when molten. Dropping down to our phosphorus, up again to our sulfur, bigger, down to our chlorine, and then down to our argon. So really the only quirky bit is there. I don't need to worry too much about that. Talking general points here, the rest of them. But you are expected to be able to explain what's happening across the period here, and certainly the different type of bonding that's present. And also, really, really important, they expect you to know that phosphorus is P4, sulfur is S8, chlorine is Cl2. That is expected of you. So, as far as I'm aware, that is the periodicity topic covered. I hope that's been of some help.